Hello again. We're still balancing half reactions in acidic media, but there's a subtle difference with reactions like this that are called disproportionation reactions. And the way you tell you've got a reaction like this is you only have one reactant. You start with a single species, and yet somehow two different things happen with it. And this doesn't make a lot of sense in its unbalanced state, but what we're talking about is there are going to be two MnO4s. And it's curious that they gave this a -2 charge. MnO4 is normally -1 charge, but all right, we'll take this at face value. The idea is we're going to have one of these MnO4 2 minuses, which becomes the MnO2, and then another one, which becomes the MnO4. So you get two of the same chemical, but different things happen to them. That's the disproportionate part. If you think of proportionate as meaning fair or equal, and disproportionate as being the opposite of that, like unfair or unequal, then this is two MnO4 2 minuses that get treated unfairly or unequally. Even though they are the same, they have different experiences. One does this, the other one does that. Now that we've written those reactions, absolutely everything is going to happen the same way as in the other half reactions we practiced. So if you're good at those, you will find this pretty comfortable. One manganese, one manganese, one manganese, one manganese. That's all balanced. Now we look at oxygen. 4 on the left, 2 on the right. This needs 2 more oxygens. 4 on the left, 4 on the right. No need for oxygen. 4 hydrogens on the right side of this thing, so the left needs 4 hydrogens. No hydrogen, so no action required there. And now we come to charges. -2 plus 4 would be +2 charge on the left of this and no charge at all on the right, so the left side needs 2 electrons to drag it down. And here we have -2 on the left, -1 on the right. -1 is actually higher, so this side needs an electron to drag it down. You can write E minus or you can throw a 1 in front, whatever you like. Now, if we are to balance this, we need equal numbers of electrons, so this 2 to 1 thing is no good. We're going to double the second reaction. Twice as much of that, twice as much of that, and twice as many of them. Now we can cancel our electrons, because there's 2 on either side. Can we cancel anything else? No. So now we add together all of the things on the left side. Quick note, these are both MnO4 2 minus, and we have a total of 3 of them. It is not only allowed, it is definitely encouraged to do that. Don't write 2 separate terms for this, you'll confuse people. Just add the coefficients. This is just like in math, if you had x plus 2x, you'd write 3x. 4 hydrogens. La 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 la. MnO2 plus 2 permanganates and 2H2O. Not too bad. Good. Let's do a couple more. Oh, let's do 3 more, sorry. They were not stingy with the practice when they wrote this thing. All right, so we start with an NO2, which becomes nitrate ion. And we have another NO2, which becomes nitrogen monoxide. And away we go. Nitrogens are 1 to 1 in both, so no need to fix anything there. 2 oxygens versus 3 oxygens. This side needs help. A single oxygen. 2 oxygens, 1 oxygen. We need a 1 over here. You can write 1 H2O if you wish. 2 hydrogens on the left. We need 2 on the right. No hydrogen versus 2 hydrogen. We need 2 over here. Okay, and how are we doing for charge? I have a bad feeling about the spacing here, but it'll be okay. We'll cope somehow. Total charge on the left here is 0. And here we have -1 plus 2 is +1. Right side needs 1 electron to drag it down. And here, what did I do here? Okay, I think... Okay, you should have interrupted me when I did this. When I balanced this reaction, I had 2 oxygens versus 1, so I added a single water, and that is correct. Then on this side, I needed 2 hydrogen, and so what I should have written over here is 2 H pluses. Now when we get to the charge, we have +2 on the left, 0 on the right. Left side needs 2 electrons. You might remember in a previous video I said you absolutely always have to have one half reaction with electrons on its right and another with electrons on its left. So when I got to this and I wasn't finding that I needed electrons on the left, it had to be my fault. So I just immediately went into error check mode and happily was able to find the problem. So keep an eye out for that. There should always be electrons being taken and electrons being given, or else you don't have a sensible reaction. So, can we combine these? Say no. You're right, we can't. Why not? Because the electrons don't match. When you have 2 here, only 1 here, so double the whole first reaction. 2 of that, 2 of that, 2 of that. 2 times 2 is 4, and 2 times 1 is 2. Now we can cancel the electrons, and can we cancel anything else? We have 2 water on the left and 1 on the right. We can lose a water here and lose 1 water here, leaving us with 1. And for hydrogen, we have 2 on the left, 4 on the right. We can lose 2 of these, and I don't want this to get too scribbly. We'll lose 2 hydrogens there, leaving us with 2. So now, when we combine all this, we get 2 NO2s plus another NO2, makes 3 NO2. You don't always get a 3 in reactions like this, but we've gotten it twice in a row. And we get a single H2O. I'm going to leave the 1 off just to prove that you can. On the right, we get 2 nitrate ions and 2 hydrogen ions and a nitrogen monoxide. All right. Nitrous acid turns into nitrogen monoxide, and nitrous acid turns into nitrate ion. Okay, nitrogens are 1-to-1 in both cases, so nothing to fix there. 2 oxygens versus 1, the right side needs an oxygen. 2 oxygens versus 3, left side needs an oxygen. Hydrogen, 1 versus 2, left side needs help. 3 hydrogens versus none, right side needs help. And if we look at charge, +1 on the left versus none on the right, left side is higher. And 0 on the left, +2 on the right, -1 plus 3, so right side is higher, needs 2 electrons. Can't combine them because the electrons don't match. We have to double our first reaction, so we have 2E and 2E. Double that, double that, double that, double that, double that. And can we cancel stuff? Definitely. We can cancel the electrons, as usual. 2 hydrogen versus 3 hydrogen, we can cancel 2 of those. So these are all gone, and only a single hydrogen remains down here. And water, actually same thing. We have 2 water on the right, only 1 on the left, so we can lose 1 water there, and we can lose 1 water on the right. Only 1 remains. Sorry, that's the letter H. So if we clean this up, 2 plus 1 is, we get the 3 thing again. I swear that doesn't always happen, but it sure is happening a lot with our examples. 2NO plus H2O plus NO3 minus, and a single lonely hydrogen ion. All right, last one. Chlorine can turn into hydrogen chloride, or maybe hydrochloric acid if it gets wet, and chlorine can turn into hydrogen hypochlorite or hypochlorous acid. Oh, that's HClO. Okay, where do we start? Don't say oxygen. We start by balancing the stuff that isn't oxygen or hydrogen. So 2 chlorines here, we need 2 on the right. 2 chlorines here, we need 2 on the right. Now we get into the OH charge thing. No oxygen, no oxygen. Nice. No oxygen, 2 oxygen. Left side needs help. For hydrogen, we have 0 versus 2. Left side needs help. Hydrogen, 4 versus 2. Right side needs help. And looking at charge, we have plus 2 on the left here, 0 on the right, so the left side is higher. Drag it down with electrons. And here, 0 on the left, plus 2 on the right. Right side needs to be dragged down, so we give it 2 electrons. And a lovely thing has happened. Our electrons match great. No need to fix anything. Cancel electrons. Cancel electrons. Cancel hydrogen. Cancel hydrogen. And I believe that's all we can cancel. The other nice thing that happens is, for once we don't get the 3. We get chlorine plus another chlorine makes 2 chlorines. My credibility would have taken a hit if we had gotten a 3 on every one of these. And it doesn't need any more hits. On the right side here, we get 2HCl plus 2HClO. Okay, what do you think of that as an answer? It's not bad, but if you notice, all these coefficients are divisible by 2. Writing the reaction like this would be like giving a fraction as 2 over 2. Anyone who sees this is going to think, couldn't you have reduced that? And the answer is, yeah, we could have, and we should have. If you get coefficients like this where everything can be divided by 2, do that, and you'll get the nicer reaction, Cl2 plus H2O, HCl plus HClO, which is still balanced and still makes sense. It's just lower terms, and everybody appreciates that. So, not too different, right? Disproportionation, other than the very first line where you have to use your reactant twice, follows all the same rules. They're not too bad.